Hey guys, we're Electronic Enforcers and we're Group 9 Senior Design, and we made a field signal and spectrum analysis training simulator. I'm Christian Manciso, and I was a project manager, general Unity developer. I mainly focus on player movements, menu UI systems, and asset integration.
And hi, my name is Jacob Knoll. I've also been a Unity developer, and I've worked on the spectrum analyzer, signal propagation, and just generally mechanics around the spectrum analyzer.
I'm Josh Easterling. I'm a Unity developer. I mainly worked on terrain, some menu and UI, as well as asset integration.
And I'm Connor O'Malley, and I worked on various design systems, and I focused on gameplay and multiplayer.
So what is electronic warfare? Electronic warfare encompasses offensive and defensive strategies involving the use of electromagnetic signals to disrupt, deceive, or disable adversary communication and radar systems, while also incorporating defensive measures for one's own systems. Basically, the problem is that this type of training for electronic warfare soldiers is very expensive to do in field. So in order to be able to cut costs and also keep the technology from disrupting civilian technologies, we decided to incorporate this technology into a virtual environment. Basically, Electronic Enforcers is a video game that serves as a virtual training environment in order to provide electronic warfare students in the U.S. Army a way to learn signal analysis, equipment interaction, and realistic scenario strategizing. All in all, the MVP for this project is the virtual spectrum analyzer in a virtual environment like Unity.
So we decided to separate the game into three systems or three epics. These are gameplay systems and multiplayer, player environment and UI, and spectrum analysis and signal propagation. So under these three categories, you can see the various systems that were included in our game. The bolded systems were part of our MVP, our minimum viable product, and we ended up getting all those done. The grayed out systems were systems that were stretch goals for us, but we didn't end up getting it done for this particular demo for various reasons. Uh, One of the systems I worked on was the dynamic controls, which I wanted to highlight really quickly. And this basically makes it really easy to customize controls no matter what type of device you're using per player.
Right. So in the beginning, when we were thinking, or we were imagining the Gave movement for the main gameplay loop, we envisioned it to kind of revolve around first player movement because we thought it was fairly realistic and immersive. However, upon meeting with the sponsors and the stakeholders, we decided to shift to a gameplay loop that revolved around vehicle movement because we were told that most of these trainees would actually be running these scenarios in a vehicle with their tool set. And that was the main cost that was presented to the main cost involved in these trainings is the wear and tear of the vehicles. So we decided to incorporate vehicle movement in order to up the immersion and also make it just as realistic and enjoyable as possible. And of course, we also decided to throw in third person movement to make it as immersive as possible so that the soldiers can get in and out of vehicles to comb areas that are not necessarily accessible by the Humvee.
Okay, and with respect to signal analysis, we had to develop a signal rendering pipeline that's basically broken down into four parts: a baking system that uses Python to bake the spectra of various signals into textures. Those textures can be imported into Unity. There's a propagation system that looks at, okay, well, how far is a signal from an antenna? What's the direction? Is there bounced propagation, etc.? A signal handler that just handles, okay, how does everything integrate into the gameplay system overall? And then the display, which is mostly shaders, compute shaders, etc., that displays the data in a nice, clean way.
As far as task division, we decided to use Jira. And if you remember the three epics we showed you earlier, we just separated those further into individual user stories. And this was mapped one-to-one with the user stories in Jira, so it was very organized. And we separated the sprints into 1 to 2 weeks, and tasks were assigned on a sprint by sprint basis per user.
Okay, the signal rendering pipeline can really be broken down into two parts, baked time and runtime. And in baked time, it's really using a Python script involving NumPy and SciPy to decompose a wave file, break it down to time sections, and then apply the Fourier transform, or FFT, optionally frequency modulate it, and then do some culling, some compression in order to cut down the amount of data, and then pack that into a texture. And then that texture gets sent to Unity, and you can pack those together into a texture array. At runtime, that texture array, which corresponds to a signal array, is actually it is convolved on the GPU using the propagation systems, calculations for how much of this signal, how much of that signal, and then a little bit of post-processing is done on it, and then it's passed along to the rendering pipeline where it can be displayed as a graph or in a waterfall mode, as you'll see. So, for example, this is the format for the texture. You can see the top 2 rows of pixels correspond to frequency ranges. These pixels are actually just singles. They're just floats that have been re-encoded into 32-bit colors. The top 2 rows correspond to minimums, maximums, and then the rest are just imaginary components and real components. So they're just complex values that are encoded per line, and these each row or each pair of rows really corresponds to a slice of time, right? So it's almost like playing a movie in some sense, right? You're playing out the signal over time, but you're playing out its spectrum. And we use propagation. We use probably. So let me start this slide over. Sorry. We use probabilistic propagation methods. So Unity's engine, physics engine, has built-in raycasts, and so you can randomly raycast out to the environment, find places where it hits, and then ask yourself, okay, is there a line of sight from that place that I hit to a signal? If there is, then you can take the length along that line in order to vary the amount of intensity, but that gives you a way of, for example, in this image, still being able to see a signal that is being bounced off of, even though otherwise in worse methods or in a more naive method, you wouldn't be able to. It could be occluded. Those two, the maximum and minimum row of pixels that correspond to the top 2 rows, for each of those signals, they can be taken, and then you can figure out for the spectrogram view, okay, a frequency at this point in X corresponds to somewhere in this range, or possibly doesn't. Maybe it was cold, but then that would correspond to -1. That's not important. Either way, those values can then be packaged into a texture, which then can be sampled in the convolution compute shader that's used to actually convolve these different signals. So, for example, on the left is an illustration indicating a signal texture array, right? We have multiple signals packaged into an array. We take from each one, where do we want in time to sample from, right? Take that slice of complex values, sum them, get the magnitude, process them. Maybe we want smoothing, maybe we want noise, maybe other effects, and then pass that along to the rendering pipeline, which is really just, in this case, a fragment shader, as you're going to see in the demo.
And for terrain design, we ultimately decided to do all of our development through Gaia. Gaia is a Unity asset that handles procedurally generating terrains. It allows for the developer to quickly go through and manually edit the terrain after generation so that you can get it to be as precise as you need it. It includes all the tools, cameras, and stuff that we need to go through and interact and explore the terrain as a player would, so that you know exactly what you're getting as you develop it. One thing what's really neat about it is you can intuitively change the rules and incorporate your own assets so that you can develop your own terrain as needed. And it's really easy to implement dynamic loading via quadrant toggling. So if resources is a concern, it allows you to easily conserve on them. The only downside to using Gaia is that it is not very cost effective. Our gameplay loop, that we had some issues coming up with this because a lot of things for this training is classified. The only thing that we were really provided with is that they sometimes will throw a tennis ball and have to use their toolkit to find it. So our gameplay models that basically the player is going to spawn in the map. They're free to roam around the entire map, excluding the boundaries which are set within the water. There's going to be spheres that randomly spawn within the map that will emit signals for the player to detect. The object is to find the ball emitting the correct or desired signal, and that's what we have.
All right, so to begin, on the left-hand side, you should be able to see the spectrogram window, which is displaying a waterfall mode. This displays the spectrum of the environment over time, whereas the graphical mode simply displays an instantaneous moment in time. In fact, as I drive around, as I look around as well, this display will vary according to the strength of the signals received by the antenna. There's actually additional bounced lighting that is being estimated via probabilistic raycasting, so randomized raycast of sound, and then smoothed over time to remove any jitter. If I step out here, you can see we have walking animations, we have driving, we have some nice pausing effects as well, depth of field. But in particular, let's go here and change this to this mode. You can see that I can scale in and out of this particular viewport, and in fact, I can shift the viewport around. And let's zoom in on this particular signal, which is centered somewhere around 100 miles. This is actually a frequency modulated signal corresponding to this particular sphere. In fact, let's turn on signal visualization mode. Now you can see that the signals in the environment correspond to lights, or in this particular mode, they correspond to lights. They're not visible during the normal mode. This is not something that trainees should see, but it's something that trainers and possibly debuggers would be interested in.